People have a common cultural habit of building the tallest building. Many civilized worlds, from the pyramids to the Tower of Babel, made constant attempts to build structures that overwhelm the surroundings. A prime example of this trend is the Petronas Tower, located in Kuala Lumpur, the capital of Malaysia. The tower was designed by Cesar Pelli, a famous Argentine architect. The site between the two buildings includes Surya KLCC, which is a large-scale shopping complex with movie theaters, department stores, bookstores, supermarkets, and Malaysia's first classical concert hall. Overall, the building uses shopping malls from 1st to 5th floors, 6th to 7th, 38, 43, and 84 and 88th floors are adjacent to the machine room, 41st to 42nd floors and 86th floors are adjacent to the observatory, and the rest spaces are residential facilities. Before we get into the specific issues of Petronas Tower, let's review the site analysis and the foundation. Petronas Twin Tower is located in Kuala Lumpur, the capital of Malaysia. The site was used as Selangor Turf Club and the racing track. To build this kind of high-rise building successfully, there are many conditions to consider. The first condition is the ground condition. Generally, the load by building itself flow from upper to lower level by structure like columns and core. They deliver loads to foundation and finally to the ground. But when the ground condition is not strong enough, building cannot withstand the load and collapse. Petronas Tower is geologically located in Canning Hill and Kuala Lumpur limestone area. The slope of the limestone area found by drilling was too steep, which could lead to ground subsidence if the building was constructed. So, to select more uniformly distributed ground, they moved 60 meters to Canning Hill area from the first selected site. From the boring test to analyze ground condition, 10 to 20 meter layer soil had water, and the length of piles had to be individually different to reach the Canning Hill and limestone due to the irregular slump zone. Consequently, the pile length varied from 40 meter to 105 meter and total number of 104. But another problem was that the sand layer where Barrett is located included water. The layer had loads of 1,140 kilopascal from each tower, while having not enough friction due to humidity. If the load is sustained, the building might have been cracked or collapsed. So, to increase the friction between soil, they used grub method to complete the foundation barrette by drilling down and pouring the admixture of concrete and soil. When piling and making foundation solid is over, building the high-rise twin tower in the critical ground is all set. Now, we are going to discuss the main issues from Petronas Tower, focusing on the high-rise building. First, we are going to look into the core system of Petronas Twin Towers. Through this semester, we thought that high-rise building is most important issue dealt with Petronas Tower. So, we are going to look after several factors that plays important role in high-rise building. Petronas Tower was the highest building when it was first built, and also now have reputation of the highest twin tower. The first important factor as high-rise building is the core system. This is the floor plan of Petronas Tower. The core system is belt-shaped structure that plays role in vertical transportation and resistance in lateral load. They use single zone and central core, which is most stable and neat structure. It is also called tube-in-tube structure, where inner core takes 50% of load and rest 50 is resisted by concrete column and core wall by outrigger system. Core system consists of lifts, exit stairs, and HVAC services. Core system is important because the usable space in building is decided by the core space ratio, which is ratio between floor and core area, especially in high-rise building. To resist larger lateral load, the increase of core area is needed, which leads to smaller floor area. The Petronas Twin Tower has a large vertical transport system divided into lower and upper floors with sky lobbies. In the case of skyscrapers, the size of the core becomes too large. They adopted sky lobby system as a solution to maintain core space ratio and maximize usability. And there are 16 perimeter concrete columns which are effective in resisting vertical load. These high-strength concrete columns have bigger weight and volume which are more effective in stability than steel frame. Along the concrete columns, there are concrete ring beam which enables the connection to columns. Due to concrete's higher vibration damping value and weight than steel, concrete beam can have enough strength. And there are bustle frame which are similar to ring beam. Bustle is a small, circular 44-story annex attached next to the main tower. Since there is no core space in the bustle, it not only brings about a change in elevation shape, but also has main effect of securing a reduced dedicated area due to the massive core. The steel deckplate structure covered with concrete slab was selected due to the economic efficiency and the stability. This system solved the difficulties of the 450-meter skyscraper by taking advantage of the steel and concrete. The mass and stiffness of concrete are taken advantage of in resisting lateral loads, and the advantage of speed of erection and long span capability of steel are used in the floor framing system. As an extension of core system, outrigger system is also important issue in high-rise building. The structure in case of high-rise building is composed of core structure in the middle and perimeter columns around and outriggers connecting the two. Outrigger is lateral structural system to improve the lateral stiffness and strength of high-rise building. To increase the efficiency of the lateral system, the inner core and exterior frame are tied together by a two-story outrigger truss at level 38. So if the vertical load is applied to building, core structure takes 50% and the other 50 is distributed to perimeter column by outrigger. Outrigger and core system is fully tied with belt truss, which allows other 12 parameter columns to be connected with core to resist lateral load. Outrigger system can reduce overturning moments down to 40%. The structural action of outrigger system is based on tension and compression. Outrigger and braced frame transfer force from core to outrigger columns. In short, outrigger system reduces the overall building acceleration due to high winds and improves occupant comfort. Next, we will discuss about the construction process of Petronas Tower. We selected skybridge and taper shape as main issues of the building. First, let's go over with the skybridge. Before construction, they had some problems. Skybridge had enormous size and weight of 800 tons. This means 200 Asian elephants are hanging in height of 177 meters. In this context, Samsung C&T and Gukdong Engineering built the world's highest two-story skybridge and successfully constructed without any accidents in process. Then, let's look into the reason constructing skybridge is difficult and how they solved the problem. Skybridge is mainly composed of main girder, skybridge leg, and support. In construction process, it was challenging to build supporting leg to support the bridge against lateral wind load. The wind load was extreme between two towers due to the tunnel effect. So there was a 50-year cycle wind tunnel testing in 3 types to construct successfully. By the wind tunnel test, the type that had 4 different legs in direction had been chosen due to its longest yielding time to resist lateral wind load. So, the skybridge leg made of steel pipe is supported in 29th floor and rise at 63 degrees and finally complete the 2-hinge arch structure assembled in 41st floor. There were 2 major problems during the work. The first problem is to move a structure weighing 800 tons to the top. Install a jack-up system to lift the skybridge approximately 50 stories above the building. Pull the lower leg of the skybridge one by one, then fix it to spherical bearing using a control cable. Assemble the center part of the skybridge on the ground while the lower part of the bridge legs were installed. The contractor solved the problem at this time. The central part of the skybridge can be divided into 3 main parts. The first part is the end block. The end block is the part that connects the skybridge and the 2 towers. The second part is 2 leg supports, which weighs about 60 tons. The last is the central part. A total of 307 components were assembled and the basic finished material was subsequently taken. Using the jack-up system, the finished central part is raised a little higher than 41st story. The second problem was that if the wind blew more than 10 meters per sec, the work had to be stopped. Afterwards, when the wind stopped, it proceeded again. Afterwards, temporarily connect the lower and upper parts of the leg and fixed it in position after the stress test. Construction of the skybridge was completed by laying concrete on the floor of the skybridge and dismantling the jack-up system. Next, let's go over with the tapering and setback. If you look at the upper structure of Petronas Tower, it has taper shape and mid-seam pinnacle at the top. They use sloping columns in 3 floors to setback to make taper shape. This kind of sloping columns have to be considered with buckling, slip, and angular measure to use. The most important issue is the strength. Enough strength can prevent column from deflection and deformation. To satisfy these terms, high-strength concrete was used in Petronas Tower. Column has to have resistance to vertical load with internal reaction against lateral wind load when the building is under extreme wind pressure. In case of normal column, slab supports the structure by tension. There can be deformation when external load is bigger than internal reaction. However, in case of sloping column, there are same reaction for vertical loads, while it provides internal reaction by structure itself to lateral wind load. It can reduce the load resisted by slab. These tapering setback structures also include reduced wind resistance by reducing cross-sectional area of the building. Here are some interesting experimental results. We can see how directly it is affected by the lateral displacement, in effect wind load, depending on the tapering angle. In our building, we calculated about 1.5 degree, which almost doubles the reduction of lateral displacement in the absence of tapering. Lastly, we chose shrinkage and verticality as the main issue from Petronas Tower as high-rise building. Why are shrinkage and verticality is important in high-rise building? There are small deformation when shrinkage occurs in small building. But in skyscrapers, the small deformations are overlapped, resulting in large deformation. Shrinkage can lead to several problems. It can lead to the change in floor heights. And also, there can be problems with elevator construction due to dislocation of elevator rail. Finally, the curtain wall can be misconstructed due to the dislocation of the fastener. Then, let's look into the types of shrinkage. The shrinkage related to building verticality occurs in two structure members. Those are column shortening and core shear wall shrinkage. It is separated into elastic and non-elastic shrinkage. The principle of elastic shrinkage is the proportional shrinkage due to the weight itself. Non-elastic shrinkage could occur by water evaporation in concrete member. This is called drying shrinkage. And the last shrinkage type is creep. It is occurred by weight itself, not from the external load. Now, let's look into core construction process to look deeper in shrinkage. We first make the foundation solid. And then, the inner core is lifted by the self-climbing form, and the outer perimeter columns are constructed by jump form. If you look close in this picture, you can find out that the core shear wall is constructed ahead of the perimeter columns. This leads to the larger shrinkage value of core shear wall during the construction process. And the column shortening has no need for shrinkage consideration when placing slab related to core shear wall. Now, let's look at relationship of those two. Let's consider there is a columns, slab, and core shear wall. In the actual construction process, core shear wall is first placed, which leads to preceding shrinkage. If we do not consider the shrinkage and place slab, we might have serious error, as you can see in this picture. So, when constructing the core wall, we have to put camber to measure the shrinkage. With the right measurements, we can set up the reference line. Finally, we can place slab in the right position. The verticality control is done by adding shrinkage value from every 5 floor and setting reference line by compensation. Next is the column shortening. We have focused on construction process with core wall shrinkage. Heavy self-weight of building should be mainly considered with column shortening, especially for high-rise building. To measure the differential shortening accurately after 20 years from construction, they place strain gauge in vertical members like column and core wall in every floor. They placed the strain gauge in triangular shape for accuracy in case of columns. After measuring 3 years by each terms, they predicted the shrinkage after 20 years. The column shortening value from the structural engineer of Petronas Tower, TNT, is bigger than the actual measured value after 2 years. This means that Petronas Twin Tower is safely designed regarding to column shortening. Studying this building, we not only learned about Petronas Tower, but also the general educational construction method. It was grateful to get the opportunity to learn construction details. This is our final presentation, and thank you.